So as I said, and as I sort of circulated a short abstract, so what I will tell you is from a physicist perspective about some of the developments in physics which have led to things that have been of interest to people in at least enumerative geometry and so on. So I'll try to give you a flavor of what those developments have been and why that has led to surprising results. So one of the so I'll tell you a little bit of what topological strings are, but before that I wanted to say a little bit about dualities, because I think the main reason why there are these surprising relations, starting with mirror symmetry and so on, is because string theory has a number of what are called dualities, which is essentially a statement that there are two completely different looking, apparently different looking, but equivalent descriptions of a certain system or a theory or whatever. So I'll explain some of this, at least a little bit. But the basic idea is, of course, something that for a mathematician is not an unfamiliar idea. And the simplest thing which we are all exposed to, even in school, is the notion of when we describe geometry in terms of algebra. So there, of course, we could have, we spend a lot of time in high school geometry proving theorems using ruler, compasses, and the methods from Euclid. But many of those theorems, you know, are very simple if you translate it to Cartesian geometry, and it becomes an algebraic statement, which is often much easier to verify or prove than the original geometric statement, and vice versa. Sometimes things which are look very complicated from the point of view of the algebraic equations describing circles and lines and so on, become simple from a geometric point of view. So that's sort of, if you wish, one of the most primitive dualities of this kind. But this, of course, has been deepened and deepened, and we have perhaps, if I'm not mistaken, perhaps one of the deepest such dualities is the Langlands correspondence, in which you are relating very different structures, and there's a claim of a strong equivalence between things, structures in algebra, and maybe automorphic forms or whatever. So, and which leads to very surprising things, and including statement, I mean, the Tanyama-Shimura conjecture, now theorem, and so on. So it's a bit similar in string theory, and I want to sort of concentrate in this talk on a certain, what I call a ladder of dualities. So just as we went from Cartesian geometry to much more deeper statements in algebraic geometry and Langlands correspondence and so on, you can think there's a sort of a similar hierarchy or a deepening of dualities in string theory, which I will allude to, but I'll just right now just enumerate them. And it's sort of in historical order as well as in order of sort of complexity or depth. So there is something called T-duality, which is essentially in the context here called mirror symmetry. So that was the first thing, and this was what late 80s or early 90s. Yeah. Then in string theory there were these developments in the mid 90s, which were called string. Well, I should maybe call strong weak dualities. Let me call them. Which sort of relate, so to say, the strong and the weak refer to sort of the strength of interactions of the string, the fundamental string-like objects that are the base of the theory. So this was sort of 95 to 2000 or so, and my work with Kumar and Wafa, which I'll say a little bit about, was in this context. And then there were the so-called gauge string dualities, or sometimes called maybe another way to say open-closed string dualities. Or this is also maybe in the popular literature sometimes called ADS-CFT. I mean, in physics parlance, it's sometimes called the ADS-CFT correspondence, Maldacena correspondence, and so on. This is roughly from 2000 and continues. So these are, as I said, these are sort of an increasing complexity and even, I think, profundity. And I think each has revealed new mathematical, each has revealed sort of new had sort of surprising mathematical byproducts as well. And those have been in the context of simplified models of string theory, and those are the things which are the topological string theory. So there's a whole context of sort of full-fledged string theory in which all these dualities are believed to hold, but that is perhaps too complicated and has maybe, from a mathematical point of view, additional stuff which is not maybe of immediate mathematical interest. But the topological strings have a way of distilling that, distilling it to some purely mathematical or enumerative geometry related topological notions. So these dualities in the context of the topological strings give you very precise mathematical statements, which even if you don't believe the physicist's proof, at least they are precise statements which one can try to go and prove using other techniques that are available to you. So that's the broad context in which these what I'm going to talk about should be viewed. So let me say something about topological strings, So if you want to learn a little bit of string theory, it's best you invest your time in studying topological strings. They are mathematically perhaps best defined and also yield sufficiently rich mathematical stuff, which has still not yet been completely unraveled. And it encapsulates in a very simplified form many of the features of the full string theory. Often the full string theory is not analytically computable beyond some simple cases, but in this topological string context, they are often solvable, so you can explicitly write down many things, and that's a virtue which will be very useful in checking at least many of these statements, and were important for sort of framing the conjectures and the statements that are made here. Okay, so any questions about that? The general philosophy. Okay, so at least at the crude level, string theory can be viewed, just the full-fledged string theory, though I won't say very much about it, but I'll just say a couple of words just to sort of give the context. So as a caricature, you can view string theory as a theory of maps from a world sheet. This is what is often called a world sheet, which is a Riemann surface of genus G. It can have punctures as well, but let me stick to the case without punctures. It can, in fact, also have boundaries, but let me, for the simplest case, view something without punctures, without boundaries. And you can view string theory as sort of a theory of maps from this world sheet to a so-called target space-time, which is some manifold M, some manifold with usually, and in many of the contexts here, it will be you can view it as a Calabi-Yau manifold. It's a 3 complex dimensional Calabi-Yau manifold. You can let me call this X here. So this is a theory of maps, meaning you're embedding this Riemann surface inside this manifold. And the basic, so this is what is called the target space. Because it's the place where this gets embedded. The basic quantity of interest is the so-called partition function or amplitude. Amplitude is a term from quantum mechanics for sort of which captures the dynamics of the system, so given this picture, the quantity that is of physical interest is the amplitude, which you define for fixed genus G as very heuristically. So this will be even on a physicist point of view quite heuristic, but you sum over maps, sum over all possible maps or all possible ways of embedding this into that times an integral, in this case over the moduli space of Riemann surfaces of genus G. If you had punctures and boundaries, you would look at the corresponding one. Well, to be more precise, it should be probably the compactified moduli space. You integrate over moduli space something which is which you give a weight, which is roughly e to the minus the area here, which is basically the pullback of so when I say the area of this thing, it's basically the pullback area under this map F of sigma. So if you want to be very concrete, you can think of this map F as you can give some coordinates xi on the manifold. Let me call it xi. You give a set of coordinates, and then you give some coordinates on the Riemann surface, let's say sigma A. And these maps are specified, if you want, explicitly in terms of telling you how xi is a function of sigma A. And the area here is just in terms of the induced metric from this map from the from this map with the Kähler form or the area form in the target space. Yeah. What exactly are we? X, which this xi? X is the manifold, so the maps can be specified by giving, let's say, in coordinates something like this, some collection xi of sigma, where I goes from 1 to d, the dimension, and then the area is something roughly like, supposing there's a metric g in, let me write it in coordinates, gij of x. This is in the target space, so then you pull back, so you get del I, del A, and then you take the determinant square root of this. So this is the this would be the pullback of the area in the area element here, sort of pull back with this metric. Typically, yeah. So, of course, so what you mean by the sum over maps is a little bit more tricky in the sense that the physicists have a way in terms of this Feynman path integral, where you sum over, you sort of integrate over all the xi's, these xi's with some measure, which we'll see in the topological string context. This will simplify and it will be relatively better defined. But the more general thing is a functional integral, which mathematicians find very uncomfortable dealing with. So that's why I won't talk so much about this general context. But this is so you can. In this sense, you're summing, let's just assume you're summing over all possible, not just necessarily smooth embeddings here. By the way, the reason this is called a world sheet is that a string is a one-dimensional object, and so when it traces out in time, a trajectory traces out a two-dimensional surface, and that surface is what's called the world sheet. If you had a point-like particle, it would have traced out a line, and which is called the world line. But for the string-like object, it's a two-dimensional surface in the world sheet. So these are sort of, if you wish, the analog of closed world lines. These are closed Riemann surfaces. If you had punctures or boundaries, they would be more like this. So this is like a cylinder, but that's the simplest world sheet you can think of. But the ones I'm considering here are sort of the analog of closed world lines, which is a sort of a signature for quantum. When you have closed loops, those are the virtual particles. Strings are breaking. That's what interactions correspond to. They correspond to a single string breaking up into two strings. or vice versa, depending if time is going this way, then you can think of the string breaking up into two strings or two strings fusing into a single string. Those are what correspond to string interactions. So you can always do a pair of pants decomposition of the Riemann surface and view it as a sum over basic individual interactions like these. And you normally give a weight for each such interaction, vertex. This is the analog of in a point particle, whirl line would go and split into two. It's a vertex on a graph there. So that's why when people do quantum field theory, they're talking in terms of Feynman diagrams, which are graphs or based on whirl lines. But when you're talking of string theory, you're talking about whirl sheets. And the basic interaction, which was like a point-like interaction with a vertex there, is now a pair of pants in the string theory. Okay, any other questions? No, I haven't told you what topological string. This is a caricature, as I said, of a general string theory. That's why it has this sum over maps, which I haven't defined, and so on. This is the sort of full-fledged string theory, and this is one of the basic quantities you compute in that string theory. But I'll define what the topological string is momentarily. Yeah. No, so here it's all maps. So in the physicists, okay, let me, so really right now I'm saying this is a caricature of the full string theory. So even though I gave topological strings as a header, this is a kind of a 2-minute introduction to what full string theory is, so that you then know when we specialize what we are specializing to. But here it's all maps. So that's why the full string theory is perhaps, it's much more much more complex, of course, and you have to integrate over all these maps. By the way, just some terminology, physics terminology, which may be useful. This is sometimes called the genus G free energy. Never mind the term, it comes from statistical mechanics and so on. And then there are other things which maybe I'll say a little later, what are called correlation functions, but this is just the terminology for this. And this kind of action with these sort of, this is, by the way, what is called action in physics terminology. A quantum mechanical amplitude has a weight, and the weight is typically exponential or something, and that thing in the exponent is called the action. So this is the action for a string. This class of actions in which it's the area which is weighting. So each map is weighted by an exponential of the area. This class of actions, these are called nonlinear sigma models. So you might have come across these terminology, but again, if the individual terms don't make any sense, don't worry. But it's a historical term. It's called nonlinear sigma model, or sometimes abbreviated in this way. Yeah. So this was, as I said, the caricature of the physical string theory. I should maybe full or physical, meaning the one that is of primary interest to physicists, is that. But what Witten did is around 88 or so, was to sort of simplify this into a baby version, from at least a physicist's point of view, a much simpler version, in which you make a few, in which you simplify this in a couple of ways. Firstly, the X I will call M, which because we'll take it to be a Kähler manifold. So instead of taking X to be some general arbitrary space manifold, we'll take it to be one with a complex structure, a Kähler manifold more generally. And in fact, often for reasons which are, which maybe I'll say something, Calabi-Yau manifold with 3 complex dimensions, so 6 real dimensions. That happens to be a very magic dimension from a string theory point of view. But some of the statements can be made more generally. So that's one simplification that we'll make. The second is that F will restrict to holomorphic maps. So of course, and this is something that's anyway used even here. You use the complex structure on the Riemann surface, and you use the complex structure now that you have a Kähler manifold. You can then talk of holomorphic maps. So these maps here are now if you give a local complex coordinates here and here, these will be holomorphic maps. Then you have xi and xi bar, and then the xi will be a function only of the z, and the xi bars will be function only of z bars. So that's what locally holomorphic maps. Actually, Witten didn't impose this by hand. There's a way of doing this, writing. What he actually did was, so to say, look at not quite this nonlinear sigma model, but he added an extra term to this nonlinear sigma model, which allowed him to then use ideas of localization. And when I say localization, this is like the localization that is used in mathematics, I guess, Atiyah and Bott and Duister-Matt and Heckman and so on. What he could show is that in that theory, this integral localizes onto holomorphic maps. So you don't really even have to, you don't have to sort of don't have to just by fiat say that we are looking only at holomorphic maps. What you find is that, so this happens, so I cannot explain it, of course, more detail, but so the path the sum gets sort of contributions only from holomorphic maps. Sorry? It's like a stationary phase, but it's like in the localization. It's not an approximation. It's an exact statement. So you can, the usual, in the usual localization ideas, you have typically some circle actions, and then you localize to the fixed points of that circle actions. It's sort of similar here, except that it's in a Grassmannian, uses the Grassmannian coordinates, and then the localization. There's a sort of a nilpotent operator, which this integral gets its contributions only from the fixed points of that nilpotent action, which turn out to be the holomorphic maps. But that, maybe I don't expect you to understood that, but if you wish, just imagine that for some reason we just restrict ourselves to these holomorphic maps, and then this corresponding quantity, the nice thing is that then this object, this thing that the physicists are interested in, called the amplitude, this Fg, becomes a mathematically interesting object. It basically becomes a generating function for enumerating the number of holomorphic maps from the genus G surface to M. So it becomes a generating function in the following sense. Let me say it a little bit more precisely. So basically what I'm saying is that this FG will essentially count for you the number of holomorphic maps from sigma G to M. Now, of course, when I say the number of holomorphic maps and count, that assumes that these are discrete, but that's only sometimes the case. Very often there is a continuous moduli space of holomorphic maps, and then what you're essentially counting or enumerating is an appropriate integral over the appropriate moduli space, and these are what are called the Gromov-Witten invariants, which, from a physicist's point of view, this is what is counting the Gromov-Witten invariants. Perhaps you have a different way of viewing them, but so basically, these objects are essentially the generating functions for the Gromov-Witten invariants of genus G. So they are, again, people probably normally talk about the genus 0 case, G equal to 0 case, where you just have a sphere. And a lot of work is, a lot of the explicit results are for that case, but you can define it in general. So let me just say it a little bit more precisely. Probably will still not be mathematically very... so if I consider some element of the second cohomology, some cone in this positive cone in the second cohomology of M, I guess physicists, we keep going between homology and cohomology a little too loosely, but anyhow, so you'll have to pardon me if I sort of am loose with my notation. But if if you have the pullback, the F star on on the corresponding class, if it is in the class beta, then and if we denote as the moduli space of holomorphic maps of genus G to M in the class beta, in the equivalence class beta, then then what we have is that if we just compute the, again, some appropriately, basically, we compute the volume of some appropriately compactified version of this, and this is, in a way, enumerating. This is the analog of the number of holomorphic maps, so we call this NG beta. Then, basically, the FG is equal to, when I said it's the generating function, that means that it's basically generating function. So this beta is some vector, so if you wish, this beta, if this beta, we view it as some beta dot t, which is basically the integral over the so-called complexified scalar form so typically in string theory you complexify the scalar form, the usual scalar form, and there's an additional antisymmetric two form, and if you compute this, you can expand it in terms of some coordinates t. So physicists often like to write in terms of coordinates. So these ti's are basically coordinatizing the complex structure, and so this is basically telling you the generating function of the maps in various classes. So that's what this FG, this integral in this context reduces to this quantity. So this is why sometimes yeah. So you sum over all the so the t is coming because supposing you choose some basis of that, and then you expand in. So now this is these are t's are arbitrary complex numbers. So really, yeah, I guess I shouldn't have. So the beta is not over the. It's not over the integer. This thing. I mean, so the beta I are over some integer lattice, and then you sum over them weighted with an appropriate. So the t's are essentially the are parameterizing the different all the elements of H2, yeah. Yes. Here, it's sort of okay. So this is the natural thing that appears in this sigma model is complexified version. So you have. So I wrote over here the metric, but actually there is an additional piece which involves this there's an additional two form which combines into this complexified in this parameter, and one of the points when that Witten observed was that you can define t and t bar, but this has essentially a holomorphic dependence on t. So that's why it's natural to consider the complexified version, so that you see that it is holomorphic in this parameter. there's something called a holomorphic anomaly. There's a T-bar dependence which comes from some boundary contributions when you integrate over here, but I won't go into that. It's a subtlety, but the T-bar dependence is actually determined completely by the T dependence. So the T dependence is the base. So it essentially depends holomorphically on these coordinates T. So actually, yeah, when I said this, that Fg is this is strictly for the case where that Fg becomes this is for the case where M is a Calabi-Yau threefold. But you can define it more generally, and the point is that if I have a d-dimensional scalar manifold, this of, let's say, of dimension d, complex dimension d, then the so-called, I guess you would call it as a virtual dimension, whatever, is given by something like this. It involves the genus G, the complex dimension, and the first Chern class of M. So in the case of the Calabi-Yau spaces, this is 0, and for d equal to 3, so this is 3 complex dimensional, this is also 0. So this has, its virtual dimension is essentially 0, which is why you can think of it as essentially counting, but this is just a sort of a virtual dimension. In general, like in all index theorems, it's that's the generic case. But so this is mathematically something natural, and that's why this Fg of t is a quantity, because these, I guess, are the things that you would be interested from an enumerative geometry point of view. So by the way, yeah, this t is sometimes called the complex scalar parameter. That's the terminology, at least that physicists use. So this is, so you can think, this is, if you wish, a sum over beta I, and something like this. So this is from this generating function you can read off the different ng beta if you could compute this. But for genus 0, I just wanted to add a footnote. For g equal to 0, one adds a so to say classical term, which is not exponential, but which is so this is the triple intersection number in that basis, and in this basis, and so it's a Ti, Tj, Tk over these parameters. So there's a piece which is sort of cubic in the T's, and then pieces which are exponential in the T's. And this is these pieces. Sometimes these are called world sheet instantons. But again, the terminology is just a physics terminology. But if you see a physics paper which says the world sheet instanton contributions are these, they are essentially referring to these exponential terms in T, as opposed to a classical piece which is often polynomial in T. Okay, so this Fg is just one of the natural quantities of interest. There are generalizations in the full of physical string theory called correlation functions, so which I won't get into because I think I'll try to avoid. I'll just focus on this. But there are generalizations in which you basically have marked points, and then you talk about n-point correlation functions, which will be labeled by genus G and the number of marked points n, and now you will have not only this weight but something else here which is labeled by the marked points, and you have to define sort of generalizations of all these quantities, which is more complicated, but I won't talk about this aspect. So this is at least a sort of the simplest thing you would compute in this topological string. So by the way, this topological string in this way is what is called the A-model topological string. It's a terminology introduced by Witten. And the reason is that there's another topological string. There are actually two topological strings you can define starting from this. So this is it depends on how I told you that Witten added a certain term over here, which essentially helped him to evaluate this by that this integral here localized to holomorphic maps. But there were sort of two inequivalent ways of adding things there, which is sometimes called the A-type twist and the B-type twist. What I said here for the where you localize to holomorphic maps is what corresponds to the A-type twist, but there's another version which the so-called B model, which in many which I won't say so much about because at least for the point that I will mention, what is important about the B model is that it becomes even simpler than this. It's this Fg. So again, we'll take X to be Kähler manifold, let's say. And now, with this B-type twist, the F does not just even localize to holomorphic maps, it localizes to the most trivial sort of constant maps. So it's even more trivial, where basically what I mean by constant maps is where the whole genus G surface is mapped to a point so it's just a constant. As a function of the coordinates on the world sheet, this dependence, the functional dependence in this map is very trivial. It's just a constant. So that's what I mean by constant maps. So that is something very simple, and the corresponding Fg becomes actually something Fg is sort of the classical in the sense that so here I said that the Fg depends only on these, because it's holomorphic, it depends actually only on these complex scalar parameters. It actually doesn't depend on the complex structure, so I should have probably recorded this somewhere. It depends only on these complex scalar parameters, these TIs. So maybe I should So Fg is independent of the complex parameters, complex structure parameters. So we have complex scalar parameters corresponding to the sort of the area elements, but then there are the complex structure parameters which correspond to the almost complex structure that you put on the space-time on this manifold M. And so the statement that this is classical and is independent of the Kähler structure, the Kähler parameters, and only depends on the complex structure. So this becomes sort of classical, because what I mean by classical is that it becomes like classical geometry. These are sort of stringy geometry, because you're sort of, it's basically how a string-like object, an extended object, is probing this, or sort of feeling this space-time. Whereas this is, because it's localizes to constant maps, in which basically everything becomes a point. That's it's just how a point would see the whole thing, which is what differential geometry, classical differential geometry is about, just probing the space-time locally using using points. So there's no area, so exactly. So these exponential terms will not be there. It will be essentially very simple. There'll be some measure pieces, so that's what I'm saying when I say it's classical. It becomes sort of very trivial. It reduces to some easily computable quantity, the analogs of these sort of triple intersection numbers and so on. But now, on the other side. So it's essentially, you're completely correct that this term is not there. So a lot of the non-trivial, this term is what gave rise to these pieces. These e to the minus beta iti are essentially coming because the beta dot t is this, and this is basically the area piece, and that's what you're computing here. So, so that's how you got this, and this is sensitive to all the Kähler parameters of the space-time. It's sensitive to the non-trivial H2 of the manifold M, but here you cannot be sensitive to the topological properties of the manifold, at least the H2 and so on. So that's what is non-trivial about this. Yes. Sorry, which one here? Mg here, Ng beta. Yeah, M is implicit. So yeah, so beta, when I write, I mean beta is sort of beta I ti. So beta is an element which is so beta I are in the integer homology, or beta is linear. Yeah. Which has this class beta I. Yes, I mean, you can think of this as an ng beta I, because if I, it's a generating function. So if I want to pick out of, so what I'll have terms like e to the minus beta 1, t1, e to the minus beta 2, t2, and so on. So it's a generating function. By looking at the t2 dependence, I can pick out a particular beta 2. So any beta that I have, I can pick out. So in that sense, it's a formal power series. So the TIs are, from that point of view, just formal power series telling you the generating function for all the beta i's. So you can view it as a collection of the beta i's. Yeah. For g equal to 1. Yeah, for a Calabi-Yau in any dimension g equal to 1, you will get something which is also, and that I think you can compute that in general. It is, yeah, I don't know how explicitly you can compute it, but it's something of interest, at least to physicists. I don't know whether mathematicians have looked at it. It's related to what is called the elliptic genus of the sigma model, but genus 1 is indeed the special also. Yes. Yeah. Any other questions? So. So the B model I won't say very much about because it's actually quite simple and relatively non-trivial. But let me finish by talking now, at least the first in the ladder of the dualities. So this mirror symmetry was at least from a physics point of view, from a string theorist point of view, it came about as a development of a simpler duality called T-duality, which I'll just very pictorially tell you. And mirror symmetry is sort of a more complicated version of that. But T-duality was something discovered in the 80s that basically, I'll just make a statement that string theory on on some S1 with radius r is equivalent to the theory on radius sort of 1 over r. So what I mean is that supposing in this x, there was a circle component of it. Let's say x was some x prime times a circle of radius r. And so the string, and when the string theory on this, when you consider the maps to this spacetime, so there's some x prime times this, but forget about the x prime won't be important. So it'll be x prime times circle with radius 1 over r. So the statement was that string theory cannot distinguish between a circle of radius r and a circle of radius 1 over r. And the reason is that unlike in a point particle where you can sort of go around and you sort of measure the length. In string theory, the string is an extended object, and what essentially happens is that the string can wind around this, and when you compute this sort of sum over all the maps, you basically get contribution from maps which will wind around this n times, and those. A winding string n times is actually the same as a string oscillating n times, meaning a string having sort of n nodes of oscillation on a circle of radius 1 over r. So a circle, so these are sometimes called n winding, and this is n momentum, and vice versa. So supposing you also have something with m nodes here, that goes to something with m winding here. So the winding and the momentum get exchanged, but if you exchange radius and 1 over the radius. So again, I don't think I can explain to you in any concrete sense, but if I compute something like this, for a space-time X which has a circle of, let's say, some radius r, what I claim is that it's the same as the same if I were to compute with another X which has in which there's a circle of radius 1 over r. So the two give you, so Fg is the same, and all other quantities are the same. So in that sense, there is a duality. You would think these are apparently distinct spacetimes, at least geometrically, if not topologically. But from the point of view of Riemannian geometry, at least, you would think these are different spacetimes, and certainly classical Riemannian geometry is what you use to describe gravity in these spacetimes after Einstein. So you would think these are different, but actually the string theory sees them as the same. So that was surprising and interesting, but perhaps not of great mathematical interest. But actually, mirror symmetry is a more sophisticated version of this. It's a more sophisticated version of this T-duality, in that now the statement is that string theory on, let's say, some x times a Calabi-Yau threefold is the same as, is equivalent to string theory, and we call it again some x prime on x prime times another Calabi-Yau threefold, which is the sort of the mirror Calabi-Yau. So just like it's a extension of this statement, like I said, you can consider string theory on some x prime times circle of radius r. It's the same as x prime times circle of radius 1 over r, but mirror symmetry is a much more sort of complex statement in which that there is a pair. There's another Calabi-Yau for every Calabi-Yau threefold, at least. There's supposed to be a pair, a mirror Calabi-Yau, and the string theory cannot actually distinguish if you compute these quantities, and I'll come to the topological strings in a moment, but I'm actually making a statement about the full string theory. If you compute any of these quantities on this or on this, you'll get the same answer. That's the statement, that this sum over maps to the Calabi-Yau or to its mirror version will be indistinguishable. And this mirror Calabi-Yau is actually topologically distinct from the original Calabi-Yau. So a Calabi-Yau threefold is characterized by two Betti numbers, H11 and H21. It's not very difficult to show. The mirror Calabi-Yau actually has its H tilde 21, H tilde 11 is H21, and the H tilde 21 is H11. So it gets switched. So the Euler number of this, the Euler characteristic of this is actually minus of the Euler characteristic of the mirror. And in fact, if unless the Euler characteristic is 0, these are clearly distinct topologically. So the Euler characteristic is essentially proportional to H11 minus H21. So that's why it gets flipped in sign. So that's a surprising statement from a string theory point of view. It was just even from a physics point of view, it was surprising that string theory sees, unlike point particles or classical differential geometry, Einsteinian gravity, you see string theories see different space-times, topologically different space-times also as equivalent. At least a class of topologically inequivalent spacetimes are somehow equivalent. And so this, as I said, is for the full string theory, but there's so this statement now you can look at what this statement implies in this context of this topological strings, because I said it's a statement of the full string theory. So the topological strings are in some sense a subsector of it where you're restricting to holomorphic maps. So you can ask what happens here, and that's where the non-trivial statement, that's where the power of mirror symmetry was first probably exhibited, and that the Fg of Ti, so let's call this Calabi-Yau as M and this as M tilde. So the M tilde is the mirror of M. Let's talk of Calabi-Yau threefolds. So if we have, so let me put a superscript to denote that this is the generating function of these enumerative invariants for M. So if I have this, there's a non-trivial statement that this is actually equivalent to M tilde of, let me call it tau I. So, okay, so let me, I have to say it like, this is a little misleading, this notation. I should probably call, let's see, what's the simplest way to, okay, let me just use the same notation, and hopefully the arguments will tell you how to distinguish this. So this is actually what you compute in the A model, as I said. But this is something that you compute in the B model. So the same Fg, as I said, if I can define the topological string B model on a Calabi-Yau, and it's just a sum over constant maps, and it's sort of, as I said, it's somewhat simple and classical. What mirror symmetry does is actually it interchanges the A model on the topological string. What it does is it interchanges the A model with the B model. So this twist under the mirror map, this twist, the A-type twist that I said over here, gets mapped to the B-type twist. So if you are looking at the topological string, so this was the statement, this was all true for the general string theory. But if you look at the topological string and you ask what happens under mirror symmetry, what it tells you is that if you compute the topological string, the A model topological string on M, that's equivalent to the B model topological string on M tilde, the mirror Calabi-Yau. This is a very powerful statement because this side, the A model, this gives you enumerative invariants, as we just discussed. But this side is a classical quantity which can actually be computed in terms of so-called period integrals. If people, I don't know how many people are familiar with the features of Calabi-Yau manifolds. One of the defining features is that there's a holomorphic middle form in a d-dimensional Calabi-Yau. There's a unique holomorphic d, 0 form. Is that something familiar to people? So that's one of the things that follows from the Yau's theorem of Calabi's conjecture, that there's a so for a d-dimensional Calabi-Yau, there's a single element of HD0, and it's a holomorphic d, 0 form. In particular, for a Calabi-Yau threefold, there's a holomorphic three form. It has purely holomorphic indices, so it's omega I, j, k, where I, j, k are the holomorphic thing, and it depends holomorphically on the coordinates. So the existence of this up to an overall factor is one of the results of this Calabi. This classical quantity, so then there are period integrals you can compute over elements of H21. Well, elements of the, I shouldn't call it over elements of H21, because that's trivial, but elements of, so if I consider AI and BI as a basis of H3 of M tilde, then I can compute these period integrals, and that's what I will call tau I, and then so you can so this is like period integrals one computes on the torus, but you have, it's the generalization on Calabi-Yau space. What it says is that there is a function. So if you define on this some kind of a symplectic basis where AI intersection Bj is some delta Ij, you form some basis of H3. So H3 has, there's the holomorphic three form, and then there are H21, H12, and then the anti-holomorphic. So there are H21 plus 1 of these. So I is going from 1 to H21 plus 1, this H21 tilde, since it's all for the So, so you can form these periods, and one of the so I don't have time to show this, but the classical geometry of the Calabi-Yau tells you that the B periods can be written in terms of a derivative of a holomorphic function of the taus. And these are sort of projective coordinates on the, so the tau you can rescale because you can multiply omega by a constant. So essentially there are only h tilde 2 plus 1 coordinates. And so these FGs, so this F0 is same thing as, so FG equal to 0 is this F0. That is that. So, so maybe the best notational compromise is to put this tilde here. So if this is not familiar, I'll just take it that this is some classical quantity you can compute on the Calabi-Yau side. It just involves knowing about various period integrals in the Calabi-Yau. And this F tilde, at least at genus 0, is the same the same thing that appears over here. So the statement is that if I know, so these taus are some coordinates over here, and this function is the thing that captures the enumerative invariance. So the thing that Candelas, De La Osa, Parks, and Green did in 1990 was to take a particular Calabi-Yau, the so-called quintic Calabi-Yau in P4, and its mirror Calabi-Yau. They knew from what the mirror Calabi-Yau was. So they could compute this quantity in the mirror Calabi-Yau for F0. They could compute this F0 there using just some classical considerations of period integrals. These obey some sort of generalized hypergeometric kind of equations. So if you see that paper, it's a very technical paper. These F's obey a fourth order differential equation and so on. And you can look at its singularities and write down, you can pin down this function, at least for F tilde 0. And besides, you can also, there is something called a mirror map, which tells you tau I as a function of these t's. So the part of the mirror thing is that there are as many of these as there are these, right? So the t's of the mirror up to projectively are the same as basically these, because h tilde 2,1 is the same as h11 of the mirror. So there are these, so there's a map between these periods, which are the quantities that you can compute in the mirror, and the scalar parameters that are, so these are complex structure parameters because they're given by some period integrals over the holomorphic threeform. The holomorphic threeform, in a sense, defines for you the complex structure on the Calabi-Yau, because it's holomorphic with respect to that complex structure. So these period integrals are parameterizing the complex structure. So they're called complex parameters. In terms of, so if you know then the map between these periods and these complex scalar parameters, which can also be worked out, then basically this equality tells you this side for M. It tells you this whole generating function, at least for genus 0. And this generating function is what people computed, and you can it gives all those magic numbers 3, 2, 7, 5, and so on, which are the for different betas. They give you the different number of rational curves. And because we are looking at genus 0 now, we are looking only at genus spheres mapped to the target space. So it counts essentially now the number of holomorphic embeddings of rational maps from rational curves into M and of different beta, you get a whole infinite prediction from basically this equality. Okay, at least I don't know if that gave you very much of an idea, but I'm happy to answer any questions you might have. But I think I'll stop here for right now.
Questions?
Scalar structures and complex structures.
Yeah, so the topological string is sort of, it is partially a misnomer. Well, it is the topological actually refers to the topological property on the world sheet. It has not so much to do with topological properties in the space-time. Though, in the end, you are kind of computing things which are fairly rigid, namely number of holomorphic maps. That is a sort of still a somewhat rigid quantity. But anyhow, the original origin of the name topological strings comes from the fact that when you do this twist in this sigma model that Witten did, that becomes a so-called topological field theory on the world sheet. But
so, for your main reason for considering Calabi-Yau threefold is that dimension is 0, and so you integrate 1 and
yeah.
Suppose you didn't have Calabi-Yau threefold, you have some positive.
Then you would have to integrate some forms.
Can you repeat this whole story?
You can repeat many of the things. You have to put in what are these endpoint correlation functions, and then you can do many things similarly.
So there is still a similar statement. Then
I believe so. I think there is a statement for Calabi-Yaus, at least, of higher dimension.
I think for genus 1, I mean.
For genus 1 also, yeah. So in arbitrary dimension also, people have, and you don't need the Calabi-Yau condition also if you. Okay, I should say one thing. I talked about the A model, which you can define on a general Kähler manifold. The B model is best defined on a Calabi-Yau space. It can be any dimension, but there's a, as far as I know, I don't know if anyone has sort of had a good way to overcome that. But people do talk about mirror maps in higher dimensions also. I don't know how successfully that has been done. But 3 seems to be the sort of a magic dimension. Yeah. For every x prime which defines a consistent string theory, there are some mild consistency conditions that x prime has to satisfy. But for any valid string theory target space, if I have any x prime, then this is true. And similarly here also, I made some corresponding statement here. Yeah.
Other questions?
Okay, if not, let's